Hello, welcome to Everything Distributed. Today we are going to talk about Bitcoin under the framework the DDoS attack is possible. And the content is based on this very nice workshop paper in financial cryptography. It's by some people from Berkeley. So what's DDoS attack? The full name is called Distributed Denial of Service Attack. And from Wikipedia, the idea is that you have multiple systems or multiple attacks that try to flop the bandwidth, try to consume all the bandwidth, the resource as some server or actually a set of server, then that causes the service to be done. So the denial of service. And the idea is that, okay, here's this illustration. You have one server that maybe you can handle one request. But now the distributed part is that I'm going to have a botnet or multiple attacker try to request something. Then either the bandwidth is not enough or your server is not big enough. Once I have more and more this kind of a request, then your server blows up, you cannot serve anything, you lose availability, you lose remedy. And that's the idea of a DDoS attack. The key observation in the paper is that actually over time, we are observing more and more DDoS attack on Bitcoin related services. And there are two main services that are mostly under attack. One is the Bitcoin exchange service, and then the other one is the Bitcoin mining. And this work is trying to study what's the relationship between DDoS attack and Bitcoin mining. And the trade-off is actually between construction and destruction. So now let's look at the model, how to model this kind of a trade-off using a very simple game-theoretical model. Then there are two choices between players, either construction or destruction. So construction is that I'm going to catch up with the market. I'm going to increase my computation power by buying more hardware, or I upgrade my hardware so that I can get more of the Bitcoin reward by mining more blocks. And destruction is that, okay, I'm going to use this amount of money or resource to launch DDoS attack to other mining pool. So the idea is that, okay, now I only have two-player game. So I have a big player B and small player S. And then the rest of market is a third party, is everything is in R. And for simplicity, this BSR also represent the respective computation power of each of the player. Then some other assumption is that assuming that everyone actually they can buy or they can invest on the same resource, so that if they do the construction part, the computation power will increase at the rate epsilon in the long run. And then the baseline model is that when you choose to launch DDoS attack, it's always perfect. You are going to be successful. And then the other party that's under attack cannot do anything of the mining. And then also assume that the cost of investment cost is negligible to Bitcoin reward. Now let's look at the simplest scenario is that everyone is investing in construction. So I keep mining. I don't think about DDoS attack at all. And then let's assume S pays off. Remember that from we talk about the mining. So what's the probability that you can successfully mine one block? That's relative. That's related to your relative computation power to the market. So remember, we have like two parties, B and S, and also everyone else, R. So the total computation power in the system is B plus R. So S pays off, the S paid off is just S. That's one block. And remember that the model assumes that in the long run, I can invest in my computation resource, and then you will increase at the rate epsilon. So S times 1 plus epsilon, B plus S plus R times 1 epsilon, 1 plus epsilon, and then actually they cancel out. So it's the same as the reward of that one block. And then if you analyze what B is going to get, it's the same thing. Okay, so that's a simple case. The other simple case is that suppose both B and S, they try to launch the DDoS attack to each other. Then because of this, they cannot do any of the mining. So the payoff, both of them will be 0. Now let's look at a more interesting case where S launches the DDoS attack and B decides to, okay, I'm not going to do anything. I just keep mining. Then in this case, actually B is paid off because that it got attacked, that the service is not available, so the payoff is 0. Then S's payoff is S over what? Now this part is a little bit different because the B's computation power is gone because it was under DDoS attack. So what you need to consider is S. And then because of the assumption of the model, when S is launching this kind of attack, it will not add more computation power into it, so just S. And the rest of the world, rest of the system, basically that they don't have anything. So they just say, okay, I'm going to keep increasing. So it's R times 1 plus epsilon because that's the rate of their improvement on their computation power. So that's the payoff for S. Okay. Then you can similarly analyze like when B is trying to do destruction and S trying to do construction. Then one very key idea for game theory is this kind of payoff matrix. So basically how you interpret this matrix is that this is the strategy for player B, this is the strategy for player S. And now the payoff for B under this scenario is here, payoff for S, the scenario is here, because like each of them has 2 strategies, so 2 times 2, that total has like 4 scenarios. So here you are going to see 4 different scenarios. Then why this matrix is interesting is that we can analyze the Nash equilibrium. So why is that Nash equilibrium cool? Is that under the case that the model is not going to change and then there's no external kind of force, then every player, in this case we have only 2 players, they have no incentive to change. So that what you are going to see is that the status quo, that it's equilibrium, then the scenario will be something predicted by the model. So what's Nash equilibrium is that you assume that each player actually know the strategy for everyone, and you also know that the strategy of the other player. Then and then you go back and look at the payoff matrix. If that once you know like this information, and then you have no incentive to change your strategy, because by changing your strategy, you are not going to increase your utility, you are not going to increase your game, then you might as well to stay at what you are doing right now. And then that's why we call Nash equilibrium. And remember here is that you can only affect your own strategy, and then you assume that you really know that what others are doing, and then that is kind of one-shot game. So now let's get back to the playoff matrix. Suppose that the small player S chooses to do destruction, DDoS attack, then what would be B's best strategy? So the way to answer this question is that you look at this payoff matrix and you say that, okay, the player S actually going to choose DDoS. So you are going to compare the strategy, the gain of using different strategy from B. So you are saying, okay, 0 and then 0. So that for B actually is indifferent between 2 strategies. So both that computation or DDoS is fine. And what this tells you is that when both parties choose to do DDoS, actually it's a weak Nash equilibrium. By that, I mean that because that, okay, once you do here 0, 0, and then no one has incentive to change the strategy. However, it's weak in the sense that because if you do get that B's paid off, both are 0. So it's possible that B say, okay, I'm going to choose computation. I'm going to choose that I'm going to invest in mining. Then now it's not a Nash equilibrium anymore, right? So it's only in the weak sense. Now let's look at that. What's the other case? Is it possible that for both parties to invest in computation to be a Nash equilibrium? And then the answer is yes, under certain relationship. So the first idea is that suppose B chooses computation. So we are going to look at this column. And we need to think from the perspective of player S, which strategy S is going to choose. So remember what's our goal? Our goal is that for S to choose computation. So we are going to check this payoff and then this payoff. And then for S to pick this computation strategy, we want this number to be larger than the bottom number, okay? And then what we are doing is to get a denominator. If this denominator is smaller, then we know that the number at the top here is larger. So that's how we get this inequality. We have B plus S plus R has to be less than or equal to S plus R times 1 plus epsilon. And then if this inequality holds, then we know that this top number will be larger. And then you can do some simplification. First, you get rid of S from both sides, and then you do some calculation. You will find out that, okay, what we actually want is that B less than or equal to R times epsilon. And then in this case, we know that S will choose computation as the best strategy under this case. And then we also need to look at B's strategy when the other player S chooses computation. But this time we are going to check the different number. Is that this B over B plus S plus R has to be larger than B over B plus R times 1 plus epsilon. Then you again compare the denominator and then you can derive that. Oh, okay, actually the inequality is that S is less than or equal to R times epsilon. So it's actually kind of symmetric. So the conclusion for this is that both parties will choose computation, and this scenario is a Nash equilibrium when these two inequality hold. Okay, and then in the paper there are other analyses like what happens if only one of the inequality holds. Then we can do some analysis to figure out that when both parties would choose to do computation. And then in reality, DDoS attack is not always successful. So what happens if this DDoS attack is not perfect? And the investment, actually that right now we assume that, okay, if you invest on your computation, you can always win or by increasing your reward, but it's not always the case. And then there might be some linear cost. And then the paper also talks about that. So that's all I want to talk about today. So the first we talk about DDoS attack, and then we look at one simple case of how to use game theory to analyze the simple two-player game between investing in your computation power and launching DDoS attack. And then we see what Nash equilibrium is and one baseline analysis. That's all. Thank you.